Cut south. All right. With a K. Fulton South with a K. All right. So antidifferentiation of a composite function. That's what we've been doing use substitution and pattern recognition with. So in general, if you have the integral of a product or a quotient, and one of the functions you see has an inside function whose derivative is the other factor, or perhaps only off by a constant multiple, something like this. You have f of g of x times g prime, such that g of x is sitting inside f. See that? F of g of x, this is your inside function. And the derivative of that inside function is the other factor. Then the antiderivative is going to be whatever the antiderivative of the outside function is, okay? So little f would be the outside function, and it determines the rule of integration. So it becomes big F of whatever the inside function is, and that little g prime, that's the one where people are like, where does it go? Where does it go? Where did the g prime go when we antidifferentiated? Well, it got packaged back up into the box, right? Because when we take the chain rule, it gets multiplied by coming out of the box. When we antidifferentiate, it gets packed back up inside the box. So it's the outside function only that determines the rule of integration. So whenever you see a product now or a quotient of two variable functions, once you find the inside function, the first step in integration is actually to take the derivative and check to see if that other factor, or it could be other factors, come from that one. There can only be one big box that contains an inside function that generates everything else, only off by a what? We can only be off by a what? Constant, multiple, okay? Not a variable. And then use substitution, of course, works. So let's try some. Example 3. Evaluate the indefinite integral of x squared plus 1 squared times 2x using u sub as well by pattern recognition. Okay, so this one's going to be pretty easy. You see a product of two functions there. What would you call the inside function? Which one looks bulkier, first of all? X squared plus 1 squared looks bulkier. Now, if you didn't identify that, or you realize that squared is something you can easily expand, you can go ahead and expand it all out and use the power rule. But if that's the bulkier function, then it's going to be possibly the one that contains the inside function. So if you look inside the outside, the obvious outside would be blob squared. Okay, you spy an x squared plus 1. Maybe that's the inside function. The inside function is what we would call u. So by pattern recognition, we mentally check. What's the derivative of x squared plus 1? 2x. Are we off by anything? No. So that 2x came from the chain rule. If you're not off by anything and you get the critical variable part, then you're ready to go to step 2. Step 2 is the rule of integration. The outside function is blob squared. So here we go. What's the antiderivative of blob squared? 1/3 blob cubed plus c. And then, of course, you just rewrite the blob. So that's doing it by pattern recognition. Very fast, very easy. Now, u substitution, again, it does have its merits, and you will be responsible for knowing how to do it. So here's how it would look. You're going to let u equal x squared plus 1. You still have to identify the inside function. You let u equal x squared plus 1. And now you're trying to change the integral from a function of x to a function of u. So I like to come down here and start replacing things. So instead of x squared plus 1 squared now, I get u squared. But I still have to replace the dx. So to replace the dx, I'm going to need the derivative. So the next thing you do is you take the derivative of both sides. Now, you could take the derivative of u with respect to x, but I told y'all last time that you could do it in what's called differential form. So you could say du equals 2x dx. And if you don't like that, you could still do it like this. The derivative of u with respect to x is 2x, and then multiply both sides by dx, and you get the same thing. Now, you're trying to replace, I guess I misspoke over here. You're not just trying to replace the dx, you're trying to replace the 2x as well. But notice, you can replace both the 2x and the dx with a single what? Du. That's nice. And so what we've done now is we've rewritten the integral into something that is pathetically easy. Remember, at this point, it doesn't matter that it's u du. It could be any variable. The antiderivative of u squared with respect to u squared, not scared, is 1/3 u cubed plus c. Now, you don't leave it like that because, remember, in this case, we introduced u as a temporary variable, as a placeholder for that complicated looking expression. So your last step then is to substitute u back in with what it's actually equal to. And if you forgot, just look up there. It's x squared plus 1. All right, so both methods work. Both methods work. The pattern recognition is very quick, very easy. You're essentially doing u substitution in your head, and instead of calling it u, you're calling it blob. Or I call it blob. You can call it whatever you want. All right, questions on example 3? All right, example 4. Evaluate the integral, blah, blah, blah. Okay, so I walk up to the problem. I notice I have a 3x, that's a variable, times sine of x squared plus 1. I notice I have a product of two variable functions. First thing I'm going to do is pull the 3 out front. If you have a constant multiple, I would recommend just pulling it out front. He's the writer. He's going to be in your final answer, and then you can combine him with any of the factors that are there. All right, so there's no product rule for integration, but I do have a product of two variable functions. Which one looks bulkier? The sine one. Yeah. And so what could be the possible inside function? X squared plus 1. And what is it inside of? It's inside of the sine function. So sine would be the outside function, and then the inside function would be x squared plus 1. So that would be what you're calling u. Let's do it by pattern recognition first. If this is what we're calling the blob, or u, what's the derivative of x squared plus 1? 2x. When you compare it to the other factor, do you get 2x? No. But it's okay. If you get an unwanted number that's multiplied, that's fine. You have to get the critical variable part, and we do. We're just off by a 2. So once you realize you're only off by a 2 and you get the x part, you're ready to go. The 3 goes along for the ride. If you're going to generate an unwanted 2, what do you have in your answer to neutralize it? You have the reciprocal of that unwanted number every time, a 1/2. And that takes care of step 1. Now you move on to step 2, which is the antiderivative part. What is it inside of? It's inside of the sine function. What's the antiderivative of sine? Negative cosine. Good. Of the blob. Plus c. Don't forget your plus c. So again, in this case, you're going to have one of each of the representative types of factors that you're going to have. You're going to have what I call the writer. He's there in the beginning. He's there in the end. He's going along for the ride. You have your correction, which is pretty important. That's the reciprocal of any one unwanted number you have from the derivative of your inside function. And then you might have like a rule. Like we've memorized that negative is really a correction as well, but it's a rule maybe we've memorized. The power rule, remember, also generates a constant. And so what you do in the end is you just combine them all, and you get a negative 3/2. Cosine of x squared plus 1 plus c. And there you go. So you don't have to take that 3 into consideration. Even if it were a 2, you could pull the 2 out front, say it's there, and now you're off by a 2, you have a 1/2 correction, it would divide out. So you still have the option of doing that. And of course, if you check by taking the derivative, you'll see that you get that. All right, let's do this one by u substitution very quickly, and then we'll probably abandon u substitution for a while until it's needed. What would you call u? U would equal x squared plus 1. All right, so down here, I'm going to have my 3 out front already, and I'm going to replace the sine part with sine of u. So what's left to replace? Well, I need to replace my x dx. The 3's going along for the ride, even in u substitution. But now I'm looking to replace my x and dx. So I take the derivative of both sides in differential form. Du equals 2x dx. Well, notice that if I'm looking to replace x dx, I can solve that for x dx by multiplying both sides by a 1/2. So I get 1/2 du equals x dx. And now I can replace those last two little pieces with the 1/2 du. Well, I'm going to put the du as the right bookend, and then the factor of 1/2 I'm going to put out front. And so now I'm left with 3/2 the integral of sine of u du. And so again, this is what u substitution is all about. It puts it in terms of a simple integral, in this case a trig integral. What's the antiderivative of sine? Negative cosine of u plus c. But there's always that one last step, right? U is a temporary variable. We now have to replace u with what u is. And what is u? U is x squared plus 1. And u is a good x squared plus 1. If u is x squared plus 1, be the best x squared plus 1 you can be. And we got the same answer through a formal process, okay? So this bullet points just kind of reminds you of what I've been saying then. You're going to have at most 3 types of constant multiples in the in your answer in the end. Some that were there in the beginning, some that you've added as a correction, and then some that are there from rules. Combine them all in the end, and don't forget your plus C. All right, example 5. These all look familiar. Have we done these already? Or maybe I did them last year. I don't know. Yeah. All right, evaluate. What would we do first? Yeah, good. Pull a 1 over pi out front. Pi is a constant, but don't just pull a pi out. Pull a 1 over pi out front. Now you get an x times an x squared plus 1. We're going to do this one entirely by pattern recognition if we can. Now notice in this case we could expand it out because it's only squared, but if that had been like a 22, you wouldn't want to do that. What would the inside function be? X squared plus 1. So I'm keeping it the same one each time so you can kind of see how the rule of integration could be something different every time. That's definitely the bulkier of the 2 factors. That could be the inside function. We mentally check. What's its derivative? 2x. Ah, that's where that x came from. It came from the chain rule. But we're off by a what? We're off by a 2, so we're going to have a correction of 1/2. And once you have that settled, you're done. Go ahead and say it's 1 over pi goes along for the ride. You have a correction of 1/2, and now you focus on the second part. What is your inside function inside of? It could be inside of anything. It could be inside of a sine. It could be inside of a radical. In this case, it's inside something squared. How do we integrate something squared? 1/3 something cubed, and that something just gets rewritten. So there it is again. The 1 over pi is the rider, the 1/2 is the correction, and the 1/3 is your constant multiple from the rule. When you can combine them all up in the end, you get 1 over 6 pi times x squared plus 1 cubed plus c. Now in that case, you might want to put it back in, the format in which it originally came with the constant in the bottom. Not necessarily, though. It wouldn't be wrong. But that's equivalent. And, of course, at any time, if you're not sure if that is the right answer, what can you do? Take the derivative, right? Shorthand sweet. Shorthand sweet. Shorthand sweet. Any size will do. Okay. I almost feel like I should put a different Mad Guide up tomorrow because today's was just too short and sweet. It's too short and sweet. Right? It wasn't that fun. Yeah. Huh? It's a leap year. Yeah. I tried to write the limerick today using the word of the day, but there's not many words that rhyme with nonce. So it's the best limerick I could make this morning, using the word nonce. Chance. Oh, by chance. Oh, yeah. That makes the limerick more funny. Yeah. Yeah. Anyway. Yeah. Okay. Anyway. Example 6. Example 6. Each of the following have the same inside function but a different outside function. We're going to evaluate each of these indefinite integrals. So you walk up to the function. You got the indefinite integral of 5 times sine of 2x times e to the cosine of 2x. So what are you going to do with the 5? Get out of there. And now you got sine of. I'm going to add grouping symbols around the sine of 2x or on the 2x because grouping symbols can help you see layers just as if you were taking the derivative. There you go. You have a product of 2 variable functions. Only one of them can be the big box that contains the inside function whose derivative, fingers crossed, is all the other factors, bless you, except possibly only off by a constant. So which factor is bulkier, the sine of 2x or the e to the cosine of 2x? Yeah, so what would be the inside function? Cosine. What does it mean to be inside an exponential function? It means to be in the exponent. Yes, yes. That's a great question. I was thinking that when I wrote that down that I would probably need to put like some kind of grouping symbol there when I type it up on a test or something. Yeah, because otherwise it would be very easy to think of all of that as one big angle. You're right. So with me here to interpret what I meant, that's a lot easier. But yeah, you would have to have something there. Thank you. And the problem wouldn't work if that whole thing were the angle. So I will have to come back. I'm going to add actually an open parentheses there as well around the A, and maybe put that in parentheses. Yeah, good. All right, so now that we know that this is what it's supposed to be, cosine of 2x should be the inside function. We check. Where did that sine of 2x come from? Did it come from the derivative of the inside function when someone took the derivative by the chain rule? Well, let's see. What's the derivative of cosine of 2x? Negative sine of 2x times what? 2, right? This one has its own inside function. So the derivative of cosine of 2x is negative 2 sine of 2x. We get the critical sine of 2x part. We're only off by a what? A negative 2. But if you're only off by a constant, you've got it. So here we go. 5 goes along for the ride. If we're off by a negative 2, we have to have a correction of negative 1/2. Always the reciprocal. Good. And now the sine of 2x is gone. It gets packaged back up, right? Now part 2. What is the cosine function inside of? It's inside of the e function. And what's the antiderivative of the e function? The e function itself. And then plus c. And then you simplify that, of course. Negative 5/2 e to the cosine of 2x. Take the derivative if you're not sure. Mentally, maybe in the beginning when you're doing this, it could be helpful. All right, the next one. We have 7 sine of 2x, and again, the 2x is the end of the angle, and then all of that is going to be times the cube root of cosine of 2x dx. So the 7 is going to come up front. We got a sine of 2x. If you see cosine of 2x squared with the cube root, I would recommend writing it as cosine of 2x, and then all to what power? 2/3. Good. So rewriting it, combining those two layers into one. Of course, the second one, I hope you would agree, looks bulkier. So it contains the inside function. And what would you call the inside function? Cosine of 2x. Once again, we check. What's the derivative of cosine of 2x? Negative 2 sine of 2x. We get the critical sine of 2x part. We're only off by, once again, a negative 2. So the 7 goes along for the ride. We have to have a correction of negative 1/2. And now the sine of 2x gets packaged back up. Part 2 of the problem, what is the inside function actually inside of? What is the rule of integration? Well, it's inside the blob to the 2/3. That's going to be a power rule, right? So by the power rule, I'm going to leave a little space. Blob to the 2/3 becomes blob to the 5/3 with the what in front? 3/5. So there's your rule constant multiple. And then, of course, the blob just goes right in there. So this is by pattern recognition. But U substitution still works. Okay? Because every time you do U substitution, you're only off by a constant. You're going to be able to solve for sine of 2x dx. And it's going to end up being a 3/5 du. Okay? So that's why the U substitution works. It gets rid of that other factor. We just say it gets packaged back up. Plus c, right? Now, if you wanted to simplify any of this mess, nothing really divides out. Negative 21/10. You could put it back under the radical. You could say it's cosine to the 5th of 2x. So maybe something like that is a simplified version. Kind of fun going backwards, huh? Kind of. I like it. Better than Sudoku. Better than Sudoku. Letter C. You try. On your mark, it said go. I'll add the grouping symbols where I intended them to be so you won't think the angles are uncomfortably large. A lot of 2's in this one. plus c. If you're on a free response and you're not sure what the answer is, bless you, don't leave it blank. Put some expression there and put plus c. X plus c. There you go. If you know that there's going to be units, make up a number. Don't put x feet squared. Put like 5 feet squared. Okay, this one here again, I brought the 2 out front, sine of 2x. I rewrote the cosine squared in the condensed format to this. And now the cosine is the inside function. Again, we're off by a -2. 2 goes for the ride, -1/2 correction. And now it's a power rule again, but this time we generate a 1/3 blob cube, bring it down. So, getting the hang of it, starting to see the patterns. A, B, C, D. Here's D. Sine of 2x times sine of cosine of 2x. Whoa. Here's one factor. Here's the other factor. The second factor looks more complicated, right? So it's going to be the one that has the inside function, which is cosine. We're off by a -2. Surprise, surprise. There's no rider in this case. That's kind of surprising. Bless you. So we just have the correction, and now the sine of 2x right here, bless you, gets packaged up. It's not a power rule now. Our cosine of 2x is inside the sine function. What's the antiderivative of the sine function? Negative cosine, right? Negative cosine of cosine of 2x, the inside function, plus c. Now that's where some students kind of get mixed up. The antiderivative of sine versus the antiderivative of cosine. Sometimes they're off by a negative. If you're not sure, what could you do? Very quickly, take the derivative. Because, you know, if you take the derivative of anything that starts with co or inverse co, it's going to end up being a negative number or a negative function. Yeah, so this one ends up being 1/2 cosine of cosine of 2x plus c. It's an entirely separate thing. The inside function, what's its derivative? Did it generate the other factors? And then part 2, what is it inside of? The rule of integration could be anything that we know how to find the antiderivative. It could be nesting inside of anything. All right, sometimes we need to use some ingenuity to make it fit something that we recognize. This one looks pretty disastrous, but what I'm noticing right away is I got a 2 in the top and a 3 in the bottom that are factors that I can pull out. And I can just let them be out front and not influence what I'm doing. Now the cosine squared minus sine squared, it's under the 5th root, so I know I can write it to the 1/5 at least in the denominator, or maybe in the top to the -1/5, but I can't really do much with that right now. Definitely the radical looks like the more complicated fraction. If you brought it to the top to the -1/5, what would be the derivative of cosine squared minus sine squared of x? Would it generate just a sine of 2x? Is that immediately recognizable? No. What I'm noticing is that my angles are different, and that's going to pose a real problem. So I need to somehow get the angles to be the same. I either need to take sine of 2x and write it in terms of single x. What would that identity be? Well, there's a sine of 2x. If I used a half angle, what would that be? I think the double angle for sine of 2x would express it in terms of single angles pretty easily. Yeah, I'm just looking at the numerator first. Would that help me? Is 2 sine x cosine x going to be the derivative of that? Maybe. Maybe I could do that. Or what is cosine squared minus sine squared equal to? That's equal to cosine of 2x. Yeah. Now, either one of those observations are going to allow you to be successful. If you call the top 2 sine x cosine x, then the derivative of the bottom will generate the top, and you'd be fine. But I think it's going to be easier here if we call cosine squared minus sine squared cosine of 2x. And now doing that, you can bring the sine of 2x, or leave it in the top, and then bring the whole thing to the top by saying it's to the -1/5, so that you can use the power rule. And there you have it. So an identity. Now, which factor looks more complicated? They're both sine and cosine, but the second one is also to the -1/5 power. So it's going to contain the inside function, which is cosine of 2x, And now, once again, we're only off by a -2, so we have a -1/2 correction, and the sine of 2x goes away. It's packaged back up. Part 2, rule of integration. How do you integrate blob to the -1/5? Power rule, right? -1/5 plus 1 is 4/5, and then a 5/4 out front. Good. And then cosine of 2x slides right in there. So now, again, you have your three amigos in the front. Mr. Writer, Mr. Correction, and Mr. Rule Constant. You just put them all together now, and you get -5/12. You can say it's the 5th root of cosine to the 4th of 2x. Plus c, if you add it there, what should you do if you didn't have it on the line above? Go back and write it on the line above. Yeah. Don't just put it at the end. If you forgot to write it, don't just add it to the end. As soon as you find the antiderivative, your integral and the dx go away, and you need either the plus c for an indefinite integral or your little evaluation bar for a definite integral. Otherwise, it's wrong in the process. Okay. On your mark and set, you go. You try. I'll do the first step for you, pulling that 11 out front, but that's as far as I can get. And then I get confused. Oh, I found a way. Y'all keep going doing it your way. Huh. I hope you're not looking at mine. That doesn't feel right. Don't look at mine. Huh. I know the instructions said we have the same inside function on all of these, so which of those two factors looks more complicated, though, in this one? That's pretty arguable, right? They're both plain old trig functions, sine and cosine. They have the same inside function, and one of them is not necessarily inside anything more complicated. So if you follow the rule of the instruction for this whole problem, then you would say that cosine of 2x is still the inside function, as it has been. But what is it inside of? It's inside something to the first power, right? So it would just be like u if you substituted it. Well, if you did that, then the derivative cosine of 2x, you're going to be off once again by a -1/2. So 11 would go along for the ride. You'd have a correction of -1/2. Your sine of 2x would get packaged back up. And then step 2, the antiderivative of blob to the first would be, well, it'd be 1/2 blob squared, or blob squared divided by 2. So you get that, and then plus c, right? And if you simplify all that, you get -11/4 cosine squared of 2x plus c. So that one works well. But did anyone choose a different inside function? Could we choose a different inside function? Well, let's see. If I bring that 11 out front again, what if I instead said that sine of 2x was now inside something to the first, and cosine of 2x was the other factor? Just kind of flipping the tables. I couldn't do that above because they had exponents already, but when they're both 1, does it work this way? What's the derivative of sine of 2x? Cosine of 2x times 2. So we get the critical cosine of 2x part. We're only off now by a positive 2. So now the cosine of 2x can get packaged back up. The 11 goes along for the ride. We're only off by a 2, so we have a correction of a positive 1/2. And now it becomes, by the rule of integration, 1/2 blob, which is now sine of 2x squared plus c. And that ends up with being positive 11/4 sine squared of 2x plus c. So is that the same answer we get over here? Are those equal to each other? Really? Cosine squared is the same as sine squared? Can two functions have the same derivative, right? That's just how we would check. We would take the derivative of this and the derivative of that. Can two functions have the same derivative but be different functions? Sure, like x squared and x squared plus 5, right? They both have derivatives of what? 2x, right. Both of these functions I came up with have derivatives of 11 sine of 2x cosine of 2x. It doesn't mean that they're equivalent. They could be equivalent, but if they're not equivalent, they would only differ by a what? A constant. There you go. Two functions, if they have the same derivative, only differ by a constant. Can we prove that these two are equivalent except for possibly a constant? Sure we can. Let's see. Let's start with this one here. I need to somehow change the sine squared into a cosine squared. Any ideas how to do that? Papa John's Pizza? Yeah. No. How about Papa Pid? That sounds better. Sine squared is the same as 1 minus cosine squared of 2x. And if I distribute, I get 11/4 minus 11/4 cosine squared of 2x plus c, which then becomes negative 11/4 times cosine squared of 2x plus c plus 11/4. And if you compare that with this one over here, now they only differ by what? A constant, 11/4. Cool. So both answers are correct. I'm guessing that maybe if you were doing it on a multiple choice, you would preview your answer. Of course, if you did it with cosine and you needed sine, you could convert it using Papa Pid. Of course, what now can we say with that c plus 11/4? It's the ShamWow c, so it could absorb it, and you can convert it. Now, here's another way to do it. I don't know if y'all saw it this way, but it did occur to me because I had sine of 2x times cosine of 2x. I knew that if there were a 2 out in front, I could condense it using a double angle identity. But I didn't have a 2, and I couldn't borrow one from the 11 because 11, right? So here's what I did. I pulled the 11 out, and I multiplied by a clever form of 1 called 1/2 times 2. Yeah? Pretty clever? I pulled the 1/2 out front with the 11, and I left it as 2 sine of 2x cosine of 2x, which condenses down by the double angle identity to sine of twice that angle. So twice 2x is 4x. This now gives me, it's still pattern recognition, but it's a single factor. And what's the inside function? 4x. So you could still have a problem that's pattern recognition or U substitution, but you only have one variable factor, but it would have itself an inside function. So here the inside function is 4x. What's the derivative of 4x? Sorry? 4. Do we have a 4 out front? No, but we're only off by a 4. So whenever your inside function is linear and you only have one factor, it's going to work. You're off by a 4. How do you correct an unwanted 4? Correction of a 4th. 11/2 goes for a ride. 1/4 correction. Part 2, what's the antiderivative sine of blob? Negative cosine of the blob plus c. So it does come out to be negative 11/8 cosine of 4x. plus c. Yeah. Now, how would you show that those are equivalent? Well, you'd have to use some identity, and you can do that. So just another way to do the same problem. A lot of these are going to have several different routes you can take. And remember, it doesn't necessarily mean now that they're equal. They could be equal in a different form, but if they're not equal, then they only differ by what? A constant. Because when you take the derivative, the constant goes to 0 anyway. All right, example 7. Now that you've seen some flexibility in your methods, I want you to evaluate the antiderivative of secant squared of x times tangent of x two different ways. Two different ways. Nothing to pull out front. If you ever have a condensed function like secant squared, it could be helpful, as we've already seen, to write it in the expanded form. Okay, so let's kind of do the first one together. We'll talk through it. If you write it like that, now the secant squared obviously looks like the more complicated of the two factors, right? But then you'd have secant as the inside function. What's the derivative of secant? Secant tangent. Oh, we get the tangent part. We're only off by a secant of x. So can I have a correction of 1 over secant of x? No, we can't have corrections of variables because when you take the derivative to check, now you have a quotient rule, not a constant multiple. Bummer. So that doesn't work. So, now we have to kind of change it a little bit. I guess maybe then what's the option? Maybe tangent's the inside function, huh? It would be inside something to the first. That's not always a real obvious one. Well, let's try it. I'm kind of running out of things here. What's the derivative of tangent? Secant what? Squared. Oh, secant squared, the whole thing, secant squared. What are we off by? Nothing. We found it. Secant squared, you're getting packaged back up. There's no correction. There's no writer. We have blob to the first. It becomes blob squared plus c, and that's tangent. So we end up with tangent squared of x plus c. 1/2. Oh, yeah. I was about to check and catch it, but you caught it because I really wasn't about to check. But you want to get in the habit of checking because it's going to get so routine and easy that you might make some careless mistakes. And if it's not, putting the plus c, it could be easily that constant multiple in the front. Thank you. 1/2 tangent squared. Now, that's just one way to do it. I claim there's another way to do it. So think about it. See if there's another way to do it. Y'all kind of play around with yours. I'm going to play around with mine. I know they're not logs, but they're still fun. Just mathematically doodling here, exploring. Not really knowing where it's going to lead me, but I'm up for the adventure. Anyone find a different way? U sub. Did you do it? What'd you call U? You called U secant squared x, and it worked? No. Oh, you tried it. Okay. Yeah. I was thinking some kind of identity. So I replaced secant squared with 1 plus tangent squared. And I quickly said, okay, and now I have two factors. The derivative of 1 plus tangent squared is not tangent. So then I distributed and I got tangent plus tangent cubed. Now tangent, seems like we know the derivative of that, right? It's secant squared, but we really don't know the antiderivative of it yet. But I can call it sine over cosine. And sine over cosine is the same as 1 over cosine times sine. So focusing on that piece right there, notice 1 over cosine times sine makes cosine an inside function. It's in the denominator to the first power. What's the derivative of cosine? Negative sine. Ha ha ha! I'm only off by a negative. So when you're off by a negative, you have a negative correction. Now when your inside function is in the denominator to the first power, that would be like replacing that with u. That'd be 1 over u. What's the antiderivative of 1 over u? The natural log of the absolute value of u. So that's actually one you're going to have to memorize. If you want to memorize it right now, there you go. What's the antiderivative of tangent? Negative natural log of the absolute value of cosine. But if you forget it, you can derive it by splitting tangent up. Now that helps you with that term, but tangent cubed, I'm stuck. Because the derivative of, you can't just say it's 1/4 tangent of x to the 4th, right? Because the derivative of tangent on the inside generates a secant squared, which ain't out there. So as fun as that was, it didn't get me anywhere. So what else can we do? What are we going to do? Roses are red, violets are... Break it up into sine and cosine. Oh, yeah, when in doubt, put it in terms of sine and cosine. I like that. 1 over cosine squared times sine over cosine. And that gives you 1 over cosine of x cubed times sine. Oh, nice. Pretty slick. So that gives us cosine of x to the negative 3rd times sine. I like it. Now, cosine's your inside function. What's its derivative? Negative sine. We're only off by a negative. So I have a negative correction. Sine gets packaged up. Now the rule of integration is blob to the negative 3rd, which when you add 1 becomes blob to the negative 2. And then dividing by negative 2 is the same as multiplying by negative 1/2 plus c. Good. You did do that right. Yeah, it kind of felt, yeah, no, perfect. And you end up with a 1/2. Now cosine to the negative 2nd is the same as 1 over cosine squared, which is the same as secant squared. So 1/2 secant squared plus c is the same as 1 over 2 cosine squared. So yeah, if you did it that way, that's great. That's fantastic. That strategy for trig proofs works here as well, as long as you can manipulate it into a different form. Now there's another way to get that answer, and that's a great way to do that. I like that. You could just split secant of x up from secant squared into secant of x times secant of x, and then times that tangent of x. Okay, now watch, just by the associative property of multiplication, like that, you could actually say, and this looks weird, this is kind of counter to what I already said. The more complicated factor when you associate them that way is the second one. But it's the first one that works, because now you could say that secant is inside something to the first power. And what's the derivative of secant? Secant tangent. It generates the other factor completely. And so now there's no correction. You have blob to the first, which by the power rule becomes 1/2 blob squared. And you get the same answer that Garrett got, just a little bit quicker. But this is not a race. And you need to be effective first and then work on efficiency. So both methods work. They're both viable. Okay? And of course, both of those, the secant squared and the tangent squared, we know that they do differ by a constant because of this identity that I wrote up here. We know that we can express secant squared in terms of tangent squared. So if we wanted to, we could prove that they only differ by a constant, which is kind of nice. All right, so kind of fun, right? Kind of fun. Going backwards, and there's several different ways you can do it. All right, we've got about 5 minutes yet. Let's see if we can get 8 in there. Now, 8 looks pretty bad. And we started off this section by taking the derivative of something that had 3 different layers, and taking the derivative allowed us to recognize what the antiderivative was. We don't have that luxury here. I see a 4, which is coming out front. I got an x squared, I got a 5 to the blob, and I got a secant squared to the blob. I got 3 variable factors now. That means that 2 of the 3 have to come from the chain rule. Because again, you can only have one box, and it's going to contain the inside function whose derivative will generate all the other factors. We're only off by a constant. Which of those three factors is the bulkiest of the three? The last one, right? The secant squared. Now here you have to kind of make the decision, are you going to write it as secant quantity squared? Or are you going to leave it as secant squared? Now I think we had this discussion maybe. If you call it like that and you say it's secant, if you let secant of blah be the inside function, then the derivative of secant is secant tangent. And there's no other secant tangent out there. So that's coming in too small. So now maybe you go out one layer and you say, okay, maybe the outside function is secant squared. Do we know what the antiderivative of secant squared is? Yeah, it's tangent. So maybe secant squared is the outside function, and then maybe all this is the inside function. Well, let's check. What's the derivative of 5 to the blob? 5 to the blob, right? That's good. Times what? When you take the derivative of something that's exponential and it's not base e, you need to multiply by the natural log of the base, which is 5. Do we have a natural log of 5 constant multiple there? No, so we're off by a natural log of 5 in that piece, but that's okay. That's just a constant. Times the chain rule, the derivative of its exponent, which generates a 3x squared. Do we get the critical x squared part? Yes, we're only off by another factor of 3. So we got it. We are only off by a combined factor of 3 natural log of 5, which is not a big deal, right? So here we go. The 4 goes along for the ride. We're going to have a correction of what? 1 over 3 natural log of 5. And the x squared and the 5 to the x cubed plus 7 all get packaged back up. And now we're on to the second part, the rule of integration. What's the antiderivative of secant squared of blob? Tangent of the blob. And then, of course, plus c. And if you're not sure if that's right, once again, take the derivative, and you'll see that you generate those other factors, and all those corrections that we put in will divide out with the unwanted constant multiples. All right, last one here. Very similar here. We got a 22, which is already in my final answer. You see that? He's already in my final answer. We got an x squared, we got a sine of 5x cubed, and an e to the cosine of 5x cubed. Which of those three factors looks bulkier? E to the blob, the last one. So e is probably the outside function, and that's probably the inside function. Let's check. What's the derivative of cosine of blob? Negative sine of the blob. We get the critical sign, we're off by a negative, so I'm going to be a negative correction. I'm going to make note over here. But it has its own inside function, 5x cubed, which generates a what? 15x squared. Do we get the critical x squared part? Yes, we're just off by a 15. So we generate all the variable parts of the other factors, which is spot on perfect. We're only off by a negative 15. Not a big deal. We got it, right? 22 goes along for the ride. We have a correction of the reciprocal of negative 15, which is negative 1/15. And what's the rule of integration? Well, it's all inside of e to the blob. What's the antiderivative of e to the blob? E to the blob. And of course, what's off to the side? Plus c. All right, we'll stop right there for today. Tomorrow, we're going to derive the antiderivatives for the other 4 trig functions, tangent, cotangent, secant, and cosecant. You already saw 10a today, right? Tangent, remember, it was negative natural log, absolute value of cosine plus c. We're going to derive the others in a very similar fashion, okay? And once we derive them, then you're going to memorize the results, okay? So let's see. We're looking at maybe finishing, Monday. Actually, tomorrow we're not going to do that. I have to apologize. Tomorrow I'm not going to be here, so Mr. Peck will be here. He's my high school algebra 2 and geometry teacher. He was here before. He's actually going to teach y'all tomorrow. He's going to start here with the inverse trig because I had to give it to him in advance. So we're going to start on the inverse trig. He'll show you how to use them, and then when I come back, we'll backtrack a little bit and memorize the others, okay? So this is kind of a nice place to start because it's kind of self-contained. All right, so that'll be tomorrow. Yeah?
Why do you prefer pattern recognition over use substitution?
It's faster. It's faster, and it's better because it keeps you mentally agile. Yeah? Because you're looking for patterns. Now, use substitution works, and there is a benefit to it because sometimes we have to do it. But Yeah, I think if you get anything out of math, it's recognizing patterns. Because, I mean, if you're not even integrating the rest of your life, being able to see patterns and see how they're connected quickly. No, absolutely not. Absolutely not. I think it's a higher goal to recognize the pattern and do it mentally. It is. It's a much more formal process. So if you need to do that, like every time in the beginning, feel free to do that, but I would encourage you to try and work away from it and then doing some of that analysis that we do in formal use sub in your head.
I'm going to try to make myself do pattern recognition because speed is definitely somewhere where I could use help. So if I could do it through pattern.
Good morning. We're having RAM problems here.